on the grid characteristic numerical method and its application to seismic wave problems. So I request sir to deliver the lecture.
Thank you very much. Today we'll have our second lecture, and I will start it with pointing out one mistake that I made at the first lecture. In fact, we dealt with one specific type of the right hand, the right side in the equation. So we discussed the equation, 1D equation, when we have the function u that depends on the t, and we are dealing with the equation du over dt is equal to minus lambda u, or if lambda is equal to 1, minus u. So if lambda is equal to 1, we obtain minus u. And I told that the initial condition for the Cauchy problem is the value of function u at the initial time moment, and we denoted it as u subscript 0. And I told that it's obvious that the analytical solution of this equation is equal to the u as a function of t is equal to the u subscript 0 multiplied by the exponent of minus t plus c, where c is a constant. It is a mistake, of course. We can't have the first order derivative here and a single initial condition to fulfill and to obtain two different constants u0 and c. This is a mistake. The correct solution is ut equal to the some constant multiplied by the e minus t. If we will substitute this function to this equation, we will obtain c minus multiplied by the e minus t is equal to the minus c multiplied by the e minus t, and this is a true. To estimate the value of c, we have to substitute here 0. U subscript 0 will be c multiplied by the e to the power minus 0 equals c, and we have here the initial condition, yes, u subscript 0. So finally, the answer this Cauchy problem is ut u subscript 0 multiplied by the e minus t. This is correct. But everything else was correct, and I published the correct code. So feel free to use all of these materials that I provided to you. Okay. Today we will discuss in more details different models that we can use to describe the dynamic behavior of the medium. We started with a trivial transport equation, and I will revise this information for you because this is a crucial equation. Because the analytical solution of this trivial equation is the base of the whole grid characteristic method. So we told that we have linear transport equation. What does it mean? we have some unknown function q. In the trivial case, we have the dependence over the x in 1D and t. And the equation is dq over t plus positive value lambda dq divided by dx is equal to 0 if we have the homogeneous equation. So to pose the problem, we have to add the initial condition. So along the whole domain, let's deal with the domain start from 0 till L capital, and time started from 0 till T capital. So we want to solve the problem inside this rectangle. First of all, we have to put here the initial condition as a function of x. And we have to add one more condition. If lambda is positive, let's add here explicitly lambda is greater than 0, we have to pose one boundary condition at the left boundary of our domain here, q boundary as a function of t. Q at x equal to 0 and time is equal to the q boundary x. So we know if lambda is constant, we know the analytical solution of this equation. Q is equal to some function q subscript 0 that depends on the combination x minus lambda t. Let's substitute any function that depends only on this variable inside the initial equation. Dq over dt will give us, let's denote it like c. We'll obtain dq over dx multiplied by dx over dt. dx multiplied minus lambda, yeah, minus lambda. dq over dx is equal to the dq over dx multiplied by dx over dx, the first derivative of q multiplied by 1. If we will substitute here, so if we will try to calculate dq dt plus lambda dq dx, we will obtain dq dx minus lambda plus lambda. So this will give us 0. So this is the correct equation, yeah. So any function that depends on this combination of the x and t will give us the solution. Let's draw here this line. If we will start from this point, you can go down left and up right. And this is a characteristic curve. X minus lambda t is equal to some constant. Over this line, the solution is constant. That's why if we want to know the value here, we have to go back and bring the solution from the initial function qi. And I can write it explicitly that Q over the X and T is the Q0 over the function X minus lambda T will give us Q0. Let's point here the time moment, the previous time moment, and some point X star minus lambda T minus tau. It is equal to X star minus lambda tau minus lambda T. So we can calculate the position of this point. If you want to calculate the value here, then our characteristic curve will go out of our simulation domain, but we will have the intersection with the boundary condition. That's why only a single boundary condition at the left, particularly left boundary of our domain, is necessary. Using this characteristic curve, it is possible to calculate values in the whole domain. Yeah, so we'll go over these characteristic curves, and we will fill the whole rectangle. What we can do? If we will speak about a little bit complicated case when we have the dependence of lambda over the x. What if lambda depends over the x? What if lambda is not constant? It means that the characteristic curve will be curved. Yeah. Let's start from this point, and we will obtain over the small time tau, we'll obtain the point, and we know that along the characteristic curve, the solution Q is constant, so we can calculate the solution at this point. If we will start the next characteristic curve from the next point, we can obtain something like this one, or something like this one. So in fact, if initially we know the solution at fixed grid points, we will know, for example, with a constant spatial distance h, we will produce a set of values, or we will know the solution at the next time moment at the other spatial positions. It can give us some new grid, but this method is called the direct grid characteristic method, and for the problem when the lambda is not constant, it's not very useful because we can obtain the trend of characteristics to go at some fixed domain, and we will not be able to reproduce to calculate the solution at the other part of our domain from 0 till L. The other method was proposed when we have some nodes here, x subscript I, and we set the initial condition of these nodes after some value, small value of time. We want to calculate the values at the same spatial positions. And to achieve this, we started from this time layer, next time layer, and go back. That's why this method is called the inverse method of characteristic. We go back and find the intersection of this characteristic curve. We can deal with the not linear characteristics, something like this one, or something like this one. In any case, we will have the problem of the interpolation. We know the values at some fixed point xi. We know the values of q at some fixed point time moment tn and fixed special points xi. We will define it like q subscript n at point I. And we want to estimate the values at the same points tn plus 1 xy. N plus 1. And we know that we can go back and according to this formula, we will obtain qi at the previous time moment. Sorry. The solution at the previous time moment at some new position x star. If we have the interpolation problem, we can solve it explicitly and obtain the formula. Previously, I gave you some example with the first order interpolation. Let's go deeper and increase the spatial order of our method up to the second order. How we can do it? We know that according to the internal property of the linear transport equation, that the solution at the next time moment at the same point is equal to the q at the previous time moment, but calculated at the point xm minus lambda tau. This is the coordinate of the point. Let's try to calculate the interpolation polynomial of the second order is equal to the a multiplied by the position x squared plus b multiplied by x plus c, where we have three unknown coefficients. Let's introduce our spatial stencil. So what we have? We have here the point xm, the point xm minus 1, and the point xm plus 1. Okay. We know the values of the solution at these 3 points. Let's draw some graph, and we know this point, and this point. Q at the point m plus 1 at the current moment, Q at the point m at the current time moment, and Q at the m minus 1 at the current time moment. So let's introduce here new coordinate system, and the coordinate xm is equal to 0. The coordinate of xm minus 1 is minus h, and here plus h. Let's substitute here. We'll have 3 equations. the first equation, x equal to the 0. A multiplied by 0 plus b multiplied by 0 plus c. C is equal to the value of the function here, q m n. Let's substitute x equal to the h here. Yeah, a h squared plus b h plus c is equal to this value q m plus 1 n, and the third point x equal to the minus h, the same ah squared minus bh plus c is equal to the q m minus 1, the point n. Great. Let's solve it. We know the answer for the coefficient c. Let's calculate the 2bh is equal to the qm plus 1 n minus qm minus 1 to be 2h. Great. This is the second coefficient. And the last one, a h squared is equal to the qm plus 1 n minus c qmn minus bh b qm plus 1 n minus qm minus 1 n. Eventually, a is equal to the qm plus 1. It looks as I made a mistake, or no. C. No, it's okay. N minus qmn divided by h squared minus qm plus 1 n minus qm minus 1 n divided by 2 h squared. Yeah. So the final formula is q at the point xm t n plus 1 is equal to the q at the xm minus lambda tau t n is equal to the p2 at the point xm minus lambda tau is equal to a, coefficient a, qm plus 1 n minus qmn divided by h squared minus qm plus 1 n minus qm minus 1 n divided by 2h squared. This is a coefficient multiplied by the xm minus lambda tau plus b multiplied by bbb is equal to q m plus 1 n minus q m minus 1 n divided by 2h multiplied by the squared, x squared multiplied by the x minus lambda tau and plus c qmn. This is the final formula for the grid characteristic method, and the precision of this formula will be O over the tau squared h squared, where tau is time step and h is a spatial step. This property is the internal property of the grid characteristic method. So if I used the interpolation procedure with some specified order of precision, the same order will be the special order of the final scheme 2, because along the characteristic curve we have the ODE with 0 right side, and the solution is remains the same. So you can use the code that I provided to you to play with it. In fact, this is a solution of one of your home tasks. So you can use this material to implement the calculation inside your notebooks. Let's continue our discussion about the mathematical models, and we discussed the trivial one, but when we are speaking about wave problems, we have to go first of all in more complex rheological relationships between stress and strains, and also we have to go inside the domain of the greater dimensions, 2D and 3D problems. How we can do it? Frankly speaking, I will say that in most cases we will discuss 2D problems because of its simplicity, but you can use the same approach to obtain the full 3D equations. First of all, 2D or 3D linear transport equations. This is a trivial material, in fact. When we have in 1D dq over dt, where q is a scalar value function, dq over dt plus lambda dq over dx is equal to 0, we will have the same situation in 3D or 2D. Dq, the same scalar function, but now this function depends on x, y, maybe z, and t, plus the vector lambda multiplied by the gradient of the scalar value function q is equal to 0. In fact, dq dt plus lambda x multiplied by the dq over the dx plus lambda y multiplied by the dq over dy, and maybe lambda z dq over dz equal to 0. And to solve this 3D equation, what we can do, we can use the splitting along the coordinate axis technique. We can solve initially the equation 1 is equal to 0. Yeah, dq over dt plus lambda x dq over dx is equal to 0. Then we can go to the second equation. Equation 2 equal to 0, and initial condition obtained from the solution of equation 1. Yeah. Dq over dt plus lambda y dq over dy equal to 0, and finally use this part of this equation and this part as the equation 3 equal to 0 with the initial conditions from equation 2. Yeah, dq over dt plus lambda z dq over dz equals to 0 with the initial conditions obtained from the step 2, from the solution of the equation 2. And to solve it successfully, we have to add in 3D case, we have the cube, yeah, the cube and also time, So what we have to do, we have to set the initial conditions x, y, and z. Initial conditions at this plane, yeah, z equal to 0, x equal to 0, and this one, y equals to 0. At these three sides, we have to set three independent boundary conditions. It can depend on time, but in any case, it will give us a chance to propagate along the time. So everything else will be the same. Let's speak about the acoustic approximation. Acoustic approximation. What if we are speaking about the water? Yeah, we have the vector of velocity of the particles that depends over the radius vector and time. We have the pressure, the scalar value that also depends on the radius vector and time. And if we will write the initial equation for the fluid over the compression stress, so if we will start with the situation when we have the balance, and if we will denote V and P, the small disturbances. So P will be not the total pressure of the water, of the fluid, but also P total as a function of area T minus P at the equilibrium. We will denote it as a P small. Will be P capital. This will be the P small as a function of area T. The same is valid for V. We will obtain the second of equations. What parameters we have to use to describe the dynamic behavior of fluid under the pressure? Of course, we have material with some density, and something like bulk compression modulus or some other constant that relates the strain and stresses. I will introduce here C as the speed of the propagation of pressure waves, of P waves inside this, but you can easily calculate that C is equal to the squared root of the K, the compression modulus, divided by rho. And the system will have the view like rho multiplied by the special derivative of the vector v over the time dt plus gradient of p is equal to 0, or maybe right side as a source function, yeah, like some explosion in the water, the dependence of the external force, yeah, on the volume of the fluid. And the second equation is d pressure over dt plus rho c squared multiplied by the gradient multiplied scalarly by the vector of v is equal to 0. Great. Let's discuss this member. It will give us the divergence. So dvx over dx plus dvy over dy plus dvz over dz. Divergence. So what we have to say, let's speak about the 1D case, because the trivial one is 1D. Let's obtain the system of equation that is valid for 1D acoustic case. Rho dv x divided by dt plus dp over dx is equal to 0. This is the first equation in 1D case. And here dp over dt plus rho c squared dvx divided by dx equal to 0. What we can do, we can divide the first equation by rho, and let's do it. 1 divided by rho. And let's represent this system in the matrix form. We will introduce the new vector of unknown q functions, vx, vx and p. So we can rewrite this system in the form d over dt of the vector q element wise plus some matrix multiplied by the d over dx, the unknown vector q, is equal to 0 vector. And let's calculate 4 elements of this metric. This matrix we will denote ax. Something multiplied by the dvx over dx, 0. Something multiplied by the dp over dx, 1 divided by rho. And here something multiplied by dvx over dx, rho c squared, and 0. Let's try to solve the equation, the determinant of ax minus lambda identity matrix is equal to 0 to obtain the eigenvalues of this matrix. We will obtain lambda square is equal to the c squared. So lambda is equal to the plus or minus c. Yeah. What does it mean? We have 2 different values, and both of these values are real, not imaginary. That's why we are dealing with the hyperbolic system of equations, and we can write that ax is equal to the omega minus 1 multiplied by the matrix lambda multiplied by the omega, where omega minus 1 contains the coordinates of the eigenvectors e1 and e2. And e1 and e2, so ax multiplied by e1 is equal to the c multiplied by the e1. Ax multiplied by the e2 is equal to the minus c multiplied by the e2. The matrix lambda is diagonal, and it contains c and minus c on its diagonal. And omega is the inverse matrix for the omega minus 1. In any case, for hyperbolic system, we can obtain this basis that contains 2 real eigenvalues and 2 eigenvectors with real coefficients. So let's look at this equation. Let's multiply it, let's rewrite it initially. dq over dt plus, instead of matrix A, we will obtain this matrix production minus omega minus 1 lambda omega, multiplied by dq over dx is equal to 0. Let's say that omega depends only on the parameters of the material rho and c. That's why we can put it under the differential over x for the isotropic, for the homogeneous case. Now we deal only with the homogeneous case when material is constant in the whole domain of the interest. And let's multiply from the left this system over the omega. In this case, we will obtain here omega dq over dt plus omega minus 1 lambda d dx omega q is equal to 0. This will give us the identity matrix. Again, we can put omega under the d over dt. And if we will introduce new vector of unknowns equal by the definition to the omega multiplied by the vector of unknown q, we will obtain the system dw over dt plus lambda dw over dx is equal to 0. This is the result of our class today. What we have to say. Let's write this equation component-wise. Yeah? dw1. We remember that we have lambda in the diagonal form. D omega w1 over dt plus c, yeah, c multiplied by the d omega 1 over dx is equal to 0. And the second component, d w2 over dt minus c, yeah, we have here minus c on the diagonal, d omega 2 over dx is equal to 0. And we remember this is a linear transport coefficient with a transport equation with a constant coefficient c and minus c. So the solution we know, v1 is any function x minus ct. And here we will obtain the same result, but with the other sign, v2 any arbitrary function x plus ct. So if we know at the previous time layer the values of v1 and v2, we can calculate the values of v1 and v2 at the next time layer. And we can go back q, the vector of unknown function pressure and velocity at the next time layer is omega minus 1. This is valid because of this function. We can multiply this over the omega minus 1 from the left, and we will obtain here the identity matrix. That's why q is equal to the omega minus 1 multiplied by the omega, by the w, sorry, by the w vector. W vector over the n plus 1, yeah. And what we can write omega minus 1, and here we can write element-wise omega 1 at the x minus c tau at the previous time layer, yeah, and here w omega w2 at the point x plus c tau at the same previous time moment. This is a K formula. If we know the pressure and the velocity at the current time layer and we want to calculate the pressure and velocity at the next time layer, we start with the calculation of the W1 and W2 values according to this formula. Matrix omega is pre-calculated, so we can use it analytically. Then we will solve the transport equations for W1 and W2. For W1, let's count how many boundary conditions is it necessary to have. We are solving from 0 till L capital and time from 0 till T capital. To calculate the value here, omega 1 is here. Yeah. So first of all, we have to specify one initial condition. Yeah, one initial at this domain. To calculate omega 1 in the whole domain, we have to add here one condition on the omega 1 at left side. To calculate omega 2 for this point, we can go along the second characteristic curve here or here, but to calculate the value here, we have to go outside of the domain. That's why one condition at the right side for omega 2. So totally we have to add to our initial system two conditions, one initial condition and two boundary conditions, one at the left side and one at the right side. If we know it, we can calculate omega at the next, or W at the next time layer here, then multiply it analytically on the inverse matrix of the omega and obtain our goal, the vector of unknown at the next time layer. Okay, what if we want to describe more complex medium? For example, you can see that we have here only C, one parameter. This is speed of the propagation of the wave. And okay, in acoustic medium, we have only a single wave, pressure wave, because we can't initialize any waves by shearing the fluid, yeah, because of the internal property of the fluid. If we want to deal with shear waves too, we have to deal with the elastic approximation. The trivial one is the approximation that rely on the isotropicity of the medium parameters. So it means that the propagation velocity of waves doesn't depend on the direction in the medium. In this case, we can introduce a couple of new parameters. First of all, we have to specify the stress tensor. This is a matrix 3 by 3, xy, xz, xyy, sigma yz, and sigma zz. And here we have the same. And we will have the stress tensor, and we will have the vector of velocity, and the system that we have is rho multiplied by dv over dt plus this part is equal to 0, or maybe the external force. And also we have to describe somehow the displacement of the material points over the stress, and we are introducing one new characteristic of the mediumCijkl. This is a material tensor, and we postulate that it is valid that sigma ij is equal to theCijkl multiplied by the epsilon kl, and epsilon kl is the relative displacement. This is 1/2 of the du k dxl plus dul over duk, where u is the displacement, not the velocity, but displacement. If we are dealing with the isotropic material, a lot of parametersCijkl is equal to 0, and we can write that sigma ij is equal to the lambda multiplied by the Kronecker delta epsilon mm plus 2 mu epsilon ij. Yeah, this is a something like 3D Hooke's law. This is a stress and this is a strain. Okay, let's substitute here everything, and we will obtain the final system for the elastic medium dvi over dt. This is valid for vx, vy, and vz, minus 1 divided by rho d sigma ij over dxj. This is this member of the equation is equal to 0. For simplicity, we will not put here the external force. The d sigma ij over dt minus lambda delta ij dvm dxm minus mu multiplied by dvi over dxj plus dvj over dxi is equal to 0. Dot. And if we will introduce the vector of unknowns, that will contain sigma ij and also the whole vector of velocities, we can rewrite this system in the canonical form as previously, dq over dt plus ax dq over dx plus ay dq over dy plus az dq over dz is equal to 0. This matrices depends only on material parameters, lambda, mu, and rho. And in the homogeneous case, we can repeat our procedure. Initially, we can split our 3D system into a set of 3 1D systems. We can analyze the eigenvalues of ax, ay, and az, and we will obtain that all of these values are real. So we are dealing with hyperbolic systems. We can repeat the procedure and obtain the solution of the initial system. I will put here the answer for the question, what is the eigenvalues of the matrix AX? You can obtain it trivially. 0 minus square root of mu divided by rho plus square root of mu divided by rho minus square root of lambda plus 2 mu divided by rho and plus square root of lambda plus 2 mu divided by rho. Lambda and mu is the Lamé parameters, rho is the density, and in fact, you can see that this is a well-known value of the pressure waves, the speed of the pressure waves, and this is the speed of the shear waves. Yeah, plus and minus. So what I have to say, just a couple of words. Now we will stop at these trivial cases when we have isotropic linear elasticity theory. However, it is possible to describe a fractured medium in the same approximation, but we have to deal carefully with this tensor CIJKL, and there are a lot of different standard models like VTI model, HTI model, etc. And the most popular in the seismic survey process is the model of thin layers, horizontal thin layers. We can describe this model by vertical transverse isotropic medium, VTI. And I will put here the formula for VTI media. We have here in 2D case sigma xx, sigma yy, and sigma xy is equal to some matrix multiplied by epsilon xx, epsilon yy, and epsilon xy. C11, the coefficient of the material that consists, and the medium consists of some material. So C11 is the property, internal property of this medium. C11, C13, 0. C13 the same as here. C33 and 0. 0, 0, and here I put 2 multiplied by the next coefficient C44. Yeah. Of course, it is possible to calculate analytically the relationships for f or g of C11, C13, C33, C44 to obtain the isotropic case. Isotropic case. You can do it manually to substitute Cij to the equation lambda for lambda and mu, and you can obtain the equivalent medium. So we can use the same linear theory of deformation and stresses for describing acoustic medium, only P waves, isotropic elastic medium, 2 waves, P waves and C waves. Yeah, sure. Fractured medium, vertical transverse isotropic medium that contains numerous thin layers, and also porous medium when we have an elastic skeleton and we have some fluid inside pores. And in this case, we will obtain 3 different by modulus different eigenvalues. So we will obtain 3 different waves propagating that propagate inside the porous medium. The wave inside the fluid, the wave inside the skeleton, and some value due to the interchange of the pulse between acoustic fluid in pores and elastic skeleton in this medium. And I will show you the code that I prepared for you and comment briefly this code. And we will stop our lecture at this point. 1 second, please. Stop and share the screen. Yeah. So what you can see here. We have the acoustic model. For simplicity, we are dealing with 1D problem. And I used here SymPy. This is the modulus of the Python. This modulus is free of charge available, and you can upload it, download it easily. So we can calculate the eigenvalues of the matrix, and we can also calculate the eigenvectors. So the matrix is here. This matrix has one eigenvalue minus c and one eigenvalue c as we obtained. In 2D case, the acoustic medium will be described by three independent unknown vectors, two components of the velocity over x-axis, the velocity over y-axis, and pressure. And this system has three different eigenvalues. The first 0 and two more plus and minus c. The matrix AY will have the same eigenvalues. You can test it manually or you can run this code and obtain. If we are speaking about the elastic isotropic medium in 2D, in 2D case, you will obtain, as I put here, 1, 2, 3 different values. One is 0 and plus minus c share and plus and minus the velocity of the p wave. So my proposal for you to go deeper in this material, first of all, calculate the internal structure and eigenvalues for the matrix AY of 2D elastic problem. Here you can see the explicit form of the AX, but you can repeat it and obtain the same. And calculate the internal structure and eigenvalues of both matrix AX and AY in the case of VTI anisotropy. So calculate, investigate, or estimate the conditions for VTI medium equivalence to isotropy medium. Yeah. In fact, if you will obtain AX and AY matrices, and if you will compare this form with this one valid for isotropic medium, you will write something like C11 equal to the minus lambda plus something, or something like this one. I will share this material with you. Thanks to the Amit, you will have the access to the to this record. So I think that now we have the time to stop, and it is the second lecture, and we will have 2 more lectures in this course. Thank you for your attention.
Thank you very much, sir. Sir, if they have any questions, then either they can mail to me or mail to you.
Yeah, feel free to ask any questions, please. I think I will share at the same cloud storage the teaching aid in English, where all students can read it, all formulas. So please
Yes,
check it. Yeah,
okay.
I will share it today.
Okay, thank you very much.
Thank you very much. Shall we stop?
Yeah? Yes, sir. Yes, sir. Yes, sir.
Okay. Thank you very much.
Okay. Goodbye. Sir.
Goodbye. Goodbye,
Bye.
colleagues.
Thank you, sir.
Thank you.
If any questions, then you can mail to me or to your coordinators.
Okay, sir.
ओके
अभी
सर।
भी आप कुछ पूछ सकते हैं अगर आपको कुछ पूछना हो तो, या नेक्स्ट लेक्चर में आप अपने क्वेश्चंस प्रिपेयर करके लाइए और सर से पूछ सकते हैं। और अभी मटेरियल जो सर शेयर करेंगे मैं आप लोगों के साथ शेयर कर लूँगा। थैंक यू।
थैंक यू सर।